If we're interested in the energy of the mass on a spring, that's easy enough to find. We know kinetic energy is 1 half mv squared, and for a spring, potential is 1 half kx squared, so the total is 1 half mv squared plus 1 half kx squared. We can pick one of our earlier results for x as a function of t, and then the velocity as a function of time we get from that. When we plug them in, if we use x as a sine omega t plus phi, we get the potential energy over here, and then that would give us v as omega a cosine omega t plus phi. So we can write that. We can actually rewrite it. We can pull out the factors of 1 half and a squared, and we get this. And if we recognize that omega is square root of k over m, so k is m omega squared, we can pull out 1 half ka squared from each side, and we get that times cosine squared plus sine squared. And of course, since the arguments are the same, cosine squared theta plus sine squared theta is 1. So we get that the total energy is 1 half ka squared, and that makes sense because that's what the energy was in the first place. If we pull the mass out to x equals a, the incoming or the initial energy is just 1 half ka squared. We could have rewritten k as m omega squared and Vmax as omega a, and what we would get is total energy is 1 half m Vmax squared. So kind of like in the roller coaster problem, the total energy is moving back and forth between all potential and all kinetic, and in general it's a mix between the two. One question you may have had is, what's the point of this omega in here? Since we don't seem to have anything moving in a circle, how do we get the idea of an angular frequency? And to understand that, imagine you have, as in this picture, you have a mass on a turntable that's spinning around vertically, and look at the shadow of the mass on the floor. You can see the red dot moving back and forth, back and forth. It turns out that the behavior of the shadow, the red dot here, exactly matches the behavior of the mass on a spring. So that's the connection. Just like we have 2 pi f for our frequency equals omega, we get that same relationship here. And of course, if you look, the red dot is faster when it's going through the middle and slower at the edges where it stops to turn around. There are other kinds of simple harmonic motion besides the ones we've looked at. One of them is called the torsional pendulum, and it's used in this clock pictured below. This is called an anniversary clock for some reason. You see these 4 little spheres at the bottom that are all connected. The way this works is you wind it up by moving these things around and around. They're connected to they're hanging from a wire. You wind them up, and then when you let go, they unwind, but they overshoot their initial angle and wind up in the other direction. Then they just keep unwinding and winding over and over again until friction takes all the energy. The force that we would have on this torsional pendulum, or the torque, is linearly proportional to the angle that we wind it through, and of course it's negative since it's a restoring torque. And we get torque as negative kappa times theta, and kappa is the torsion constant, which is kind of like the spring constant, and that depends on the wire. We use Newton's second law, sum of the torques is I alpha, and we get what looks like a very simple equation, negative kappa theta equals I alpha, but this is again a differential equation. And again, we don't have to know how to solve this, but if you took this to someone in the math department, they would say this is exactly the same as your other equation. All you've done is change the names of the variables. So our solutions here are going to look exactly the same, where before we had xt is amplitude times cosine or sine omega t plus phi. We get the same thing. Theta as a function of t is theta max, the amplitude, times cosine omega t plus phi, or sine omega t plus phi. And now, instead of omega being square root of k over m, it's square root of kappa over moment of inertia. The period is still 2 pi over omega, and we can write, therefore, that it's 2 pi square root of I over kappa. This simple pendulum, or this torsional pendulum, is interesting, but it's not the most common kind. An approximation to that is the most common kind is called the simple pendulum. Here we imagine a point mass, this yellow dot, on a massless rod or string. And if we look at what forces and torques we have here, notice that we have mg pulling down and we have tension pulling back up to the upper left. The gravitational force is going to cause a torque on this mass. And since we know torque is Rf times sine of theta, we can see that the F is mg, the R is L, the length of the string, and then we get sine theta like we had before. This torque is also going to be negative since it tries to bring this mass back to equilibrium, back to straight up and down. So again, sum of the torques is I alpha, negative mgl, sine theta is our torque, and then on the right, I and the second time derivative of theta. The I for a point mass at the end of a string of length L is simple, it's just ml squared. So we can plug that in and we'll make some cancellations, and we finally get down to this. Negative g sine theta over L is d squared theta dt squared. The problem with this is not the same as the formula for simple harmonic motion. The answer for this problem, theta as a function of t, is actually what's called an elliptic integral, and it's a lot harder than we want to try and do. It turns out, though, if we keep the angle small, that sine theta and theta are almost exactly the same thing. This is called the small angle approximation. It only works if you're using radians. But you can see below, if we take the sine of 0.001, we get 0.001. The sine of 0.01 is still very, very close to 0.01. And even at 0.1 radians, that sine is less than 0.2% away from theta equals sine of theta. If we keep theta less than about 0.1 radian, which again is about 6 degrees, this will be an excellent approximation. When we make this approximation, the differential equation turns into negative g theta over L instead of sine theta on the left. This is exactly the simple harmonic motion equation again. If we go back to, since this is going to be regular simple harmonic motion, we get that theta as a function of t is theta max times cosine or sine of omega t plus phi, and this time omega is the square root of g over L. The period is then 2 pi times the square root of L over g. The very important thing here is that the period does not depend on amplitude, and that's why it's so useful. The time for one tick, for one period, doesn't depend on how far back you pulled the pendulum. If it did, it would be a horrible clock because air resistance is going to gradually slow this down and reduce the amplitude constantly. And if that affected the period, we'd have a lousy clock. The simple pendulum is simple, but it's not very realistic. A better model is the physical pendulum. This is what you use for real objects. For physical pendulum, we have this cylinder here as our object. It has some center of mass, and we're going to say we suspend it at a height h above that center of mass. There's still a torque mg trying to line it back up vertically if we let go of it, and our torque is still going to be Rf sine theta. That would give us negative mgh sine theta. We put it back in Newton's second law, and again we have to use the small angle equation if we want to get something workable. So we get negative mgh theta is I second derivative of theta with respect to time. Same solutions as before, and now omega is square root of mgh over I, and period is 2 pi square root of I over mgh. So we'll have a good clock, but only if we can keep people from pulling the pendulum out too far to the left. So if you make clocks for a living, how do you keep people from making clocks from ruining the time reliability of your clock? What you can do is make it impossible for them to pull the pendulum back too far. And the way you do that is put it in a tall, narrow case, like a grandfather clock. You can see here the pendulum can only move a little bit to the left and right before it's stopped.